Hello. Wanted to talk to you about the mechanism of oxidation reactions that we were talking about in class today, and then we talked about on Wednesday as well. Just looking at how we oxidize alcohols to ketones, aldehydes, and carboxylic acids. So the compounds that we're going to use, the reagents that we've talked about, are chromic acid and pyridinium chlorochromate, or PCC. So here's chromic acid, pyridinium chlorochromate. The way that you get pyridinium chlorochromate is that you just react pyridine, which is a base, with chromic acid. There's some chloride in there to balance the charge, and you get pyridinium chlorochromate. The key difference between these two things is that pyridinium chlorochromate is a neutral compound. There's no acid and no water present when you use pyridinium chlorochromate. It's completely neutral. When you use chromic acid is a strong acid. It's always present with water and H3O+. And this is the key to the reactivity difference. We're going to see that when you get to an aldehyde in the mechanism, which both of them go through an aldehyde, because there's no acid or water present, the PCC stops reacting. Because there's acid and water present for chromic acid, it's going to continue to react after forming the aldehyde. Right? So that's the key difference. The mechanism for both, the mechanism of oxidation, is identical. So if we look at one, we've looked at both. It's exactly the same. All right. So what I want to do is look at this reaction where we have a primary alcohol with chromic acid going to form a carboxylic acid. Right. And again, all of the oxidation options, PCC or using a secondary alcohol, are all going to look the same. All right. So let's think about what happens when we do this reaction. Right. If you think about electrophile and nucleophile, the chromium is very electrophilic. It has 4 oxygens around it, 6 bonds to oxygen. It's going to be very electron poor. The alcohol is going to be electron rich, so it's not surprising that we can have the alcohol add to the chromium, and that sort of reaction should look like when we're doing addition to a carbonyl. We have a nucleophile add, double bond to oxygen, the electrons go on to oxygen. All right, so what does that give us? So we get an intermediate that looks like that, where we've now connected the alcohol to the chromium. Right. We can now get a proton transfer reaction, right, where a proton moves from what started as the alcohol onto one of the alcohols on chromium. Right, and what will that give us? We get to that intermediate. Now in this position, or in this spot, we can lose water. So we get to this intermediate here, and now is when we can do the reaction that's going to form the first carbon-oxygen pi bond. Right? So if we do the following reaction where we have water act as the base, water can make a bond to the proton that's part of the alcohol we started with. The electrons in the CH bond can go to form a carbon-oxygen pi bond, and then the electrons in the oxygen chromium bond go on to chromium. So you'll note here that chromium is gaining electrons, right? So the chromium is being reduced, right? Leo the line goes GER, gain electrons reduction, right? So that makes sense because we're oxidizing the organic part, the alcohol. We must be reducing the chromium part, right? And that's definitely what's happening. All right, so what do we end up with here? We end up with H3O plus the chromium that's gained 2 electrons plus an aldehyde, right? Now, if this were the PCC reaction, right, we wouldn't have H3O plus, right? We wouldn't have acid, right? We'd end up in using this, we'd have Cl acting as the base, right? And then it could get neutralized by some of the O minus, right? Or we could have the O minus acting as the base. The key point when we're using PCC is that we don't have anything to further react with the aldehyde, right? In this case, we have things that can react with the aldehyde, right? And because of that, the reaction's going to keep going, right? So make yourself a note. PCC stops here, right? There's no H3O plus and water to continue the reaction, right? When we're working with chromic acid, we can continue reacting, right? And so what happens now is that the aldehyde is going to get protonated by the acid, once that happens, now water can add, right? And after a proton transfer to another water molecule, we get to something that we've seen before, right? That's a hydrate. And we saw hydrates when we were doing reactions with carboxylate anions and alkylithium. In that case, we didn't have an H here. We had an R group, some sort of carbon. And we said that the ketone was more stable than the hydrate. But when we have an aldehyde, the hydrate is more stable than the aldehyde. So it turns out that it favors the formation of this. Once this is formed, you'll note that we have another alcohol and another H that we can remove. So in the PCC reaction, we can't do this to get down to this hydrate intermediate. In chromic acid, since we can, we're going to form that intermediate, and we're going to continue to do the reaction with this and chromic acid. Right? So let's react that again with chromic acid. And so this is going to just look just like what we just did above. Do the exact same steps. We'll do a proton transfer. Now we can have water leave. We can do the same thing we did before, which is use water as the base, grab the proton that we know we have to remove to make our carboxylic acid. Those electrons go to make the carbon-oxygen pi bond. Electrons in the oxygen-chromium bond go back onto chromium, because again, we're reducing the chromium. And then what do we end up with? We regenerate acid. We get the same reduced chromium that we generated previously. And we end up with the carboxylic acid that we knew we had to produce. Right? So again, all of the oxidation reactions of alcohols go by this same mechanism. The key point being when you have chromic acid and you're in acid, you're able to form the hydrate, which can continue to oxidize one more time. All right. So again, we can understand this mechanism. This is not a mechanism that I'm going to ask you to reproduce. Oxidation reactions in organic chemistry are truly seen as tools, where if you want to make an alcohol into a ketone aldehyde or carboxylic acid, you use the correct reagent and then you continue on in your synthesis. So I hope this is helpful as you think about this reaction. And again, we can understand this, but we're not going to need to go through it when we're doing problem sets, quizzes, and exams.